Welcome back to our session. We're still talking about the energy in as far as, chemical reactions are concerned. By now, we are familiar with the energy changes that take place in an endothermic reaction. Now, we want to focus our attention on the exothermic reaction, which is the second category of the types of reaction in as far as energy is involved. Right. Now, in as far as an endothermic reaction is concerned, we are saying that more energy is actually, released than absorbed. So, if we talk of an exothermic reaction, that there is more energy that is released to the surrounding than absorbed. So that's by comparison. And then we're saying the enthalpy change, which is the heat of reaction, right? So remember, enthalpy change is the heat of reaction. In an endothermic reaction will always be a negative value. So a negative enthalpy change suggests that the reaction is actually exothermic. Okay, so in other words, if more energy is released than absorbed, it says to us that the products will be at a comparatively lower energy level than the reactants. Right. So in as far as the profile of an exothermic reaction, we realize that immediately that the products are actually at a lower energy level than the reactants. Okay. And if you look at the amount of energy released, okay, that's as much energy that is released versus the amount of energy that is actually absorbed. So we can safely say that more energy is released than absorbed. So if we say the enthalpy change in this reaction is equals to energy of products, right, less the energy of the reactants, we immediately realize that the enthalpy change will be a negative value, okay, will be less than zero, because these products are at a lower energy, okay? But that has nothing to do with, the activation energy. So it can have even lower or higher activation energy, it doesn't matter, but by comparison, more is released than absorbed, right? So then we've got certain types of reactions that are spontaneous. What do we mean when we say a reaction is spontaneous? This is the type of reaction that actually requires very little amount of energy for it to take place. But by now we know that for a reaction to take place, we need to break bonds. So if a particular type of a reaction requires very little energy, which means that this reaction can take place at a very low temperature, we would say that reaction is actually spontaneous. So this reaction will actually occur, at room temperature. So if the amount of energy that it requires is very low, then that reaction is spontaneous. Right. So then on the other end, we have got non-spontaneous reaction. So these reactions will only occur if we raise the temperature above, say, for argument's sake, room temperature. So these actually require a comparatively higher amount of energy for them to actually take place, whether they are endothermic or exothermic. And then let's look at something that's very interesting in as far as, the minimum amount of energy required for a reaction to take place. We've got a catalyst. A catalyst is actually a substance, okay, that we add onto a reaction, so that the reaction takes place very, very fast. So what a catalyst is actually a chemical substance that is involved in a chemical reaction but is not used up. So the role of the catalyst is actually to lower the activation energy. So if we have a catalyzed reaction, what we're actually saying is that we have added a chemical substance that will actually provide an alternative pathway for that same reaction to take place, but this catalyst does not get used up. So the amount of catalyst before and after the chemical change actually remains the same. But what it essentially does, it lowers the activation energy so that the reaction takes place, much quicker or at a higher rate, right? So what it does, it lowers the activation energy. So if we were to focus our attention, suppose this is the path for the catalyzed reaction, okay? Uncatalyzed rather, okay? So if we introduce a catalyst, now this is the activated complex, okay? Obviously, in the uncatalyzed reaction, there is greater amount of activation energy, okay? But then if we introduce a catalyst, the energy of the activation complex is comparatively lower, okay? But realize that the catalyst does not affect the energy of reactants or the products. That's very, very important, right? Okay, now here is a question. We want to examine an energy profile for a chemical reaction that is represented by this hypothetical reaction where A reacts with B to give us AB, okay? Right, it's a chemical change. And then the first question, before we look at the question, here is the energy profile of this particular hypothetical reaction. Remember, it's A plus B to give us what? AB. So we are reading this or interpreting it from our left to our right. So A and B are our reactants, while AB is our product. So there are given values there on the vertical axis versus the reaction progress or reaction course, right? Okay. Now the first question says calculate the activation energy for this reaction. So what are we looking for here? We're looking for activation energy. Okay, what is activation energy? Is the minimum amount of energy required for a reaction to take place. So the reactants are at an energy of 225 kilojoules per mole. So this interval to the activation complex actually represents our activation energy. So that interval 240 minus 225, it's actually 240 kilojoules. If we can just correct that value, it's actually 540, right? Okay, it's 540 minus 225, okay? Because we are looking at the amount of energy that was absorbed to break new bonds so that we reach the activation complex. That value is equals to 315 kilojoules per mole. So we need to be able to identify in this profile what represents the activation complex and then do the maths after that. So this is the minimum energy that is required for this particular reaction to take place. Right. Moving along, now we want to identify the energy of the activation complex. Okay, first of all, if we go to our profile, the highest, after supplying that minimum energy for this reaction to take place, we need to identify our activation complex. So this is our activation complex, right? Which has to do with the minimum energy that needs to be supplied for this hypothetical reaction to take place. So the amount of energy that this activation complex it has is actually 540 kilojoules per mole. Right. And then furthermore, we want to calculate the energy released. Remember, when energy is released in a chemical change, the energy of the system drops because the energy is released to the surroundings. So from that energy level, right, to that energy level, when we form the product, this has to do with the energy release. So the difference in this case is actually 540, less 100, which gives us 440 kilojoules per mole, right? Okay, so that's straightforward. That's why there's that drop in the energy in as far as the profile is concerned. Okay, and then the enthalpy change of the reaction. Enthalpy change of a reaction is energy of the product, less the energy of the reactants. Okay, that's what we know. So we read it off from the graph. The products are at 100 kilojoules per mole, less the energy of the reactants, which is 225. Okay, so when we do that difference, it would give us negative 125 kilojoule per mole. Now, this is the enthalpy or the heat of reaction. So this is a negative. What does that tell us about this type of reaction? Which takes us to the next question. So there is a negative enthalpy change in this reaction, which is less than 0, meaning that this is typically an exothermic reaction. Right. And then last but not least, if we are to add a catalyst to this reaction, what effect will a catalyst have on this reaction? We know that a catalyst actually provides an alternative pathway with a lower activation energy, right? So if that's the case, so if the blue profile represents the catalyzed reaction, you know that the activation energy will be lower. But what are the options that are given from the multiple choice? Adding a catalyst change from spontaneous to non-spontaneous? Definitely not, okay? Because whether the reaction is spontaneous or not, a catalyst just lowers the activation energy. If it lowers the activation energy, it means the energy of the activated complex becomes lower, okay? That's a change, okay? But the energy of the products, no, the enthalpy change of the reaction is actually not affected. So from 540, we would have a value that is actually less than 540. Right. So that's as far as, you know, the types of reaction and the, you know, how energy is actually involved. So from this, we need to do as much practice as we possibly can so that we can actually be more comfortable around these energy profiles and the, you know, the calculations that go with it. Okay. For now, I think we shall, because that's the time we had for today, we'll call it a day. Bye-bye for now.